Have you ever been in a car that's speeding up, but you have no idea why? Imagine you're on a long road trip. You're cruising along, but then you notice something strange. Without anyone pressing the accelerator, the car starts going faster and faster. You check the engine, you check the controls, but everything seems normal. This is exactly the situation we find ourselves in, but our car is the entire universe. It's on a journey that started 13.8 billion years ago with the Big Bang. For a long time, we thought this cosmic journey was slowing down. But what if I told you the universe is stepping on the gas? And honestly, nobody knows where the pedal is. This simple question, is the universe speeding up or slowing down, is one of the biggest mysteries in science today. It's a question that cuts to the very heart of existence itself. The answer determines not just the past of our cosmos, but its ultimate fate. Are we heading towards a quiet cold end, or a dramatic fiery finale? This isn't just an abstract thought experiment for astrophysicists in labs. The speed of the universe dictates the story of everything. It's the final chapter in the grandest book ever written, and we're just now trying to read the last page. Understanding this cosmic acceleration is fundamental to knowing our place within this vast, dynamic tapestry. Think of the universe as an enormous balloon being inflated. Every galaxy is a dot drawn on its surface. As the balloon expands, all the dots move away from each other. From the perspective of any one dot, it looks like all the other dots are rushing away. This is what we see when we look out into space with our telescopes. Galaxies are receding from us in every direction. The farther away a galaxy is, the faster it appears to be moving away. This is the expansion of the universe, a concept we've understood for nearly a century. But the real puzzle isn't that the balloon is inflating, it's the rate at which it's inflating. For decades, the story seemed simple enough. The journey began with a bang, and now the universe was coasting, gradually losing momentum. But the cosmos, as it often does, had a major plot twist in store for us. The discovery that the expansion might actually be accelerating threw a spanner in the works of everything we thought we knew. It was like watching a ball thrown into the air, expecting it to fall back down, only to see it shoot upwards into the sky with even greater speed. This baffling observation has sent us on a new quest, a detective story of cosmic proportions to uncover the mysterious force responsible for this acceleration. For most of the 20th century, astronomers were confident about one thing: the universe's expansion had to be slowing down. This wasn't just a wild guess. It was based on the most powerful, well-understood force in the cosmos: gravity. Gravity is the ultimate cosmic glue. It's the force that pulls everything together, from apples falling to Earth to stars clumping into massive galaxies. It holds planets in their orbits and keeps our feet firmly on the ground. It's a persistent, attractive force that works across the grandest of scales, always pulling, never pushing. It was the undisputed champion of cosmic forces, so the logic was straightforward. If the Big Bang was the initial explosion that pushed everything outwards, then gravity was the constant brake, pulling everything back inwards. Imagine throwing 1,000 marbles into the air. They fly apart at first, but the Earth's gravity immediately starts to pull them back down, slowing their ascent. Scientists believe the universe worked the same way. The combined gravitational pull of all the matter, every star, every galaxy, every dust cloud, should be acting like a giant anchor, gradually slowing down the expansion that started with the Big Bang. The only real question was whether there was enough gravity to eventually stop the expansion and reverse it. This idea painted a picture of a universe locked in a great cosmic tug-of-war. On one side, you have the initial outward momentum from the Big Bang, pushing space-time apart. On the other side, you have the relentless inward pull of gravity, trying to rein it all back in. For a long time, the smart money was on gravity. It seemed inevitable that this fundamental force would eventually win the battle, or at least fight the expansion to a standstill over countless eons. The universe was seen as a system that was losing energy, winding down from its explosive birth. This deceleration model was the bedrock of cosmology. It shaped all our theories about the universe's large-scale structure and its ultimate destiny. Scientists were so sure of this that their primary mission was simply to measure how much it was slowing down. By measuring this rate of deceleration, they hoped to calculate the total amount of matter in the universe, its total mass. This would tell us our ultimate fate. Would the universe expand forever, just more and more slowly? Or would gravity finally win, pulling everything back together in a big crunch? No one was prepared for the answer they were about to find. Then came 1998. It was a year that would forever change our understanding of the universe. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were on a mission. Their goal was to measure the precise rate at which the universe's expansion was slowing down. They were essentially trying to weigh the universe by observing its motion. To do this, they were using some of the most distant and powerful explosions in the cosmos as their measuring sticks. A special type of exploding star called a Type Ia supernova. They were hunting for these cosmic beacons in the far reaches of space. What they found was not just surprising, it was revolutionary. It was the kind of result that makes you check your data, recheck your calculations, and question your sanity. The data from these distant supernovae was clear, but it made no sense according to the prevailing theories. The most distant explosions were dimmer than they should have been. This dimness meant they were farther away than predicted. If they were farther away, it could only mean one thing. The universe hadn't been slowing down. In the time it took their light to reach us, the universe had expanded more than anyone expected. The expansion was speeding up. This discovery was like dropping a bowling ball on a glass table. It shattered the standard model of cosmology. The universe wasn't coasting, and it certainly wasn't slowing down. It was accelerating. This meant that the great cosmic tug-of-war wasn't being won by gravity. Some other mysterious force, a repulsive force that pushes things apart, was not only present, but was dominating the entire cosmos. It was a result so profound that the leaders of the two teams were awarded the Nobel Prize in Physics in 2011. They had set out to measure a number and ended up uncovering a whole new reality. The implications were staggering. If the universe is accelerating, it means that as time goes on, distant galaxies will be receding from us faster and faster. Eventually, they will be moving away so quickly that their light will never be able to reach us. Our cosmic horizon will shrink. The night sky, in the far, far future, will become a much lonelier place, with our local group of galaxies isolated in a vast empty void. The 1998 discovery didn't just give us a new piece of information. It fundamentally altered our vision of the future and our place within it. So, how did astronomers use exploding stars to measure the entire universe? The key lies in something we call a standard candle. In astronomy, a standard candle is any object that has a known, consistent brightness. Imagine you're in a completely dark field at night and you see a single candle flame in the distance. Is it a very bright candle far away or a dim candle close by? You can't tell. But what if you knew that all candles of this type have exactly the same intrinsic brightness? Then, by measuring how dim it appears, you could precisely calculate its distance. The dimmer it looks, the farther away it must be. This is where Type Ia supernovae come in. These are not just any stellar explosions. They are the gold standard of cosmic measurement. They occur in binary star systems, where one of the stars is a white dwarf, the dense, burnt-out core of a star like our Sun. This white dwarf greedily pulls material from its companion star. As it gains mass, its internal pressure and temperature rise. It continues this process until it reaches a very specific critical mass, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. At this exact point, it triggers a runaway thermonuclear explosion that obliterates the star. Because every Type Ia supernova explodes at this exact same mass, the resulting explosion is astonishingly uniform. Each one shines with almost the same peak brightness, releasing an incredible amount of energy and briefly outshining its entire host galaxy. They are fantastically bright, visible across billions of light years. This makes them perfect standard candles. When we spot one in a distant galaxy, we know its true brightness. By comparing this known intrinsic brightness to how bright it appears to us through our telescopes, we can calculate its distance with remarkable precision. By measuring the distance to these supernovae, we can build a map of the universe's expansion history. We also measure the supernova's redshift, the stretching of its light caused by the expansion of space. The redshift tells us how fast the galaxy is moving away from us. By plotting distance against speed for many supernovae at different epochs of cosmic history, we can see if the expansion rate has changed over time. It was this method that allowed the two teams in 1998 to discover that the distant supernovae were farther away and thus dimmer than their redshift would suggest in a decelerating universe, revealing the shocking acceleration. If the universe's expansion is accelerating, something must be pushing it. Gravity pulls, so this new something must be a repulsive force, acting like a sort of anti-gravity. Scientists have given a name to this mysterious entity, dark energy. It's called dark because it doesn't seem to interact with light or any other form of electromagnetic radiation. We can't see it, we can't touch it, and we can't detect it directly in a lab. We only know it exists because we can see its effect on the universe as a whole, the large-scale cosmic push that is driving galaxies apart from one another. So, what is dark energy? The honest answer is, we don't know. It is, without a doubt, the biggest mystery in all of physics. The leading hypothesis is that it might be a property of space itself. Albert Einstein was the first to propose something like this with his cosmological constant, a term he added to his equations of general relativity to keep the universe static. He later called it his biggest blunder when Edwin Hubble discovered the universe was expanding. But now, it seems Einstein might have been onto something. Perhaps empty space is not empty at all, but is filled with a latent energy, a vacuum energy, that creates a repulsive force. According to our current best estimates, dark energy is not just some minor component of the universe, it's the dominant one. When we add up all the stuff in the cosmos, we find that the ordinary matter that makes up stars, planets, and us accounts for only about 5% of the total energy density. Another 27% is dark matter, another mysterious substance that provides the gravitational scaffolding for galaxies. The remaining 68%, the vast majority, is dark energy. This means that the universe is primarily governed by two things that we have no direct understanding of. We are living in a cosmos dominated by the unknown. The strange thing about dark energy, if it is the cosmological constant, is that its density doesn't dilute as the universe expands. As space gets bigger, the density of matter and dark matter decreases because they are spread out over a larger volume. But the density of dark energy remains constant. This means that in the early universe, when everything was closer together, gravity was the dominant force. But as the universe expanded, matter thinned out, and the ever-present repulsive force of dark energy eventually took over, starting the era of cosmic acceleration a few billion years ago. It's a ghost in the cosmic machine, and it's now in the driver's seat. Just when it seemed the story of cosmic acceleration was settling in, a new puzzle emerged. This one is called the Hubble tension, and it's a deep and troubling disagreement in our measurements of the universe's current expansion rate, a value known as the Hubble constant. Think of it this way. We have two different, highly trusted methods for measuring the speed of a car. One method says the car is going 67 kilometers per second for every megaparsec of distance. The other method, equally reliable, says it's going 73. The difference might not sound like much, but in cosmology, it's a huge discrepancy that points to a potential crack in our understanding. The first method involves looking at the local universe. This is the technique that uses standard candles, like type Ia supernovae and another type of star called Cepheid variables, in relatively nearby galaxies. By measuring their distances and speeds, we can calculate the current expansion rate directly. This method has been refined over many years and gives us a value of around 73 kilometers per second per megaparsec. It's a direct measurement of what's happening now. It's like putting a speedometer on the universe today and reading the dial. This is our late universe measurement. The second method looks back in time to the early universe. It uses the cosmic microwave background, the faint afterglow of the Big Bang. Satellites like the Planck Observatory have mapped this ancient light with incredible precision. This map shows us the state of the universe when it was only 380,000 years old. By feeding this data into our standard cosmological model, which includes dark energy and dark matter, we can predict what the expansion rate should be today. This method gives a value of around 67 kilometers per second per megaparsec. The prediction from the early universe does not match the measurement from the late universe. This tension is a major headache for cosmologists. Both measurements are incredibly precise, and the teams behind them have double and triple checked their work. The discrepancy is statistically significant, meaning it's very unlikely to be a random error. So what's going on? Is there something wrong with our understanding of the standard candles we use? Or is our cosmological model itself incomplete? Some scientists are exploring alternative ideas, suggesting that perhaps dark energy isn't a constant, or that there might be new exotic particles that we haven't accounted for. The Hubble tension tells us that the cosmic story is far from over. The rate of cosmic expansion isn't just an abstract number, it holds the key to the ultimate fate of our universe. Depending on the nature of dark energy and the outcome of the cosmic tug-of-war, our universe could be heading for one of several dramatic conclusions. Each scenario is a direct consequence of how the battle between gravity's pull and dark energy's push plays out over cosmic timescales. It's the final act of the cosmic play, and the script is still being written by the laws of physics. Let's explore the three most likely endings. First, there's the Big Freeze, or heat death. This is what would happen if dark energy is a simple cosmological constant, and the acceleration continues at its current, gentle pace. The universe will continue to expand, and galaxies will continue to recede from one another. Over trillions of years, all the stars will burn out, leaving behind black holes, neutron stars, and cold cinders. Eventually, even these will evaporate through a process called Hawking radiation. The universe will become a vast, dark, and unimaginably cold place, a near-perfect vacuum with only stray particles drifting aimlessly. It's a quiet, lonely end. Then there's the more dramatic Big Rip. This is a possibility if dark energy is not constant, but is instead a phantom energy that grows stronger over time. In this scenario, the cosmic acceleration would become more and more powerful. First, the repulsive force would become so strong that it would tear apart clusters of galaxies. Then, it would overcome the gravity holding individual galaxies together. In the final moments, it would be powerful enough to overcome the forces holding solar systems, stars, and planets together. In the very last fraction of a second, it would even rip apart atoms, shredding the very fabric of space-time itself. Finally, there's the possibility that we got it all wrong, and gravity will eventually win. This could happen if dark energy weakens over time or is not real at all. In this scenario, the universe's expansion would slow down, stop, and then reverse. Everything would start heading back towards everything else. Galaxies would rush together, merging in a chaotic cosmic pileup. The universe would become hotter and denser, eventually collapsing back into the infinitely hot, dense singularity from which it all began. This is the Big Crunch, a fiery cosmic rebirth, which could potentially lead to another Big Bang in a cyclical universe. To solve these profound mysteries, from the Hubble tension to the true nature of dark energy, we need more data, a lot more data. We need to look deeper into space with greater precision than ever before. Fortunately, we are entering a golden age of cosmology, with a new generation of powerful telescopes and observatories coming online, designed specifically to tackle these questions. These incredible instruments are our next generation eyes on the sky, promising to peel back another layer of cosmic reality and provide the clues we need to complete the puzzle. On the ground, observatories like the Vera C. Rubin Observatory in Chile will conduct a decade-long survey of the sky, cataloging billions of galaxies and discovering thousands of new supernovae. Its unprecedented ability to map the southern sky over and over will create a time-lapse movie of the universe, allowing us to track the effects of dark energy on the distribution of matter with stunning accuracy. By observing how galaxy clusters grow over time, we can test whether gravity behaves as we expect across cosmic scales and measure the history of cosmic expansion in exquisite detail. In space, we have missions like the European Space Agency's Euclid telescope, which launched in 2023, and NASA's upcoming Nancy Grace Roman Space Telescope. These are dark energy hunters. Euclid will create the largest three-dimensional map of the universe ever made, observing billions of galaxies out to 10 billion light-years away. The Roman Space Telescope will have a field of view 100 times larger than Hubble's, allowing it to survey vast swathes of the sky and discover thousands of Type Ia supernovae. Together, these missions will provide two independent and highly precise measurements of the expansion history of the universe. These new tools will test our standard model of cosmology like never before. They will either confirm the existence of a simple cosmological constant or reveal that dark energy is something far more complex and dynamic. They will provide a definitive answer to the Hubble tension, telling us whether our current model is broken or just incomplete. This is how science works. We build a theory, we test it, and when we find a crack, we build bigger and better experiments to see what lies beneath. These future telescopes are our crowbars, ready to pry open the secrets of the cosmos. So, why does this all matter? Why should we care if the universe is expanding at 67 or 73 kilometers per second per megaparsec? Why pour billions into telescopes to study a mysterious energy we can't even see? It matters because these questions are not just about physics. They are about us. They are about our fundamental need to understand our origins, our context, and our destiny. To ask about the fate of the universe is to ask about the ultimate significance of our own existence. It connects us to the grandest possible story, a narrative that began long before we were here and will continue long after we are gone. This debate, this cosmic mystery, is a beautiful reflection of the scientific process itself. It's a story of curiosity, of challenging long-held beliefs with evidence, and of the courage to admit that we might be wrong. We thought the universe was slowing down, but we kept looking. We found it was speeding up, but we didn't just accept it. We are now testing that idea from every possible angle, searching for cracks, for tensions, for the next revolution in thought. This is humanity at its best, curious, relentless, and always reaching for a deeper understanding. The pursuit of this knowledge is a celebration of what our minds can achieve. The quest to understand cosmic expansion is also a lesson in humility. It reminds us that we live on a tiny planet, orbiting a single star in one galaxy among hundreds of billions. And it turns out that the universe is made of stuff we can't even comprehend. The ordinary matter that constitutes everything we've ever known or touched is just a tiny fraction of reality. We are the foam on the surface of a deep, dark, cosmic ocean. But the amazing thing is, from our small vantage point, we can look out and piece together the story of that entire ocean. That is the power of the human intellect. So, what do you think? Are we destined for a cold, quiet freeze, a violent rip, or a fiery crunch? Is there a mysterious dark energy pushing us apart, or is there something even stranger going on with the laws of physics? The conversation doesn't belong only to scientists. It belongs to everyone who has ever looked up at the night sky and wondered. The universe is telling a story. Let's keep listening, and let's keep asking questions, because in the end, the search for answers is what truly defines our place in the cosmos. Keep looking up.